Next up, we're going to talk about some second partial derivatives. So we're going to be talking specifically about the case of a function of two variables. So what we're going to do is let z be a function of both x and y. The first partial derivatives would be notated in one of the two following fashions. So the partial derivative of z with respect to x, or f with the subscript x of xy, would be the first partial derivative with respect to x. And dz over dy, or f with the subscript y followed by xy, would represent the first partial derivative with respect to y. If I were to differentiate either of these variables with respect to either of our independent variables, I would be arriving at a second partial derivative. Now that means that there are a total of 4 different second partial derivatives that I can get. So, starting with the first partial with respect to x, if I were to take the second derivative, it would appear in the following fashion. So if I take the partial derivative with respect to x of the partial derivative of z with respect to x, you'll see a notation that's very similar to what you would have seen in Leibniz notation in Calc 1. This would be d squared z over dx squared. This is the second partial derivative of z with respect to x, or using our alternate notation, this would be f with two partial derivatives with respect to x. Now, if I start with the first partial derivative of f with respect to x and I differentiate it with respect to y, that notation will look like this. The way that it's expressed would be d squared z over dy dx. Now, this notation can look a little bit confusing because we first started with the derivative with respect to x, then went with the derivative with respect to y. So this actually means differentiate first with respect to x, then with respect to y. This is why many students prefer the following notation: differentiate with respect to x, then with respect to y. No problem. Now, as far as this guy is concerned, if we start with the partial derivative with respect to y, we could differentiate that with respect to x. So d over dx of dz over dy, and this would be d squared z over dx dy. Now again, this means differentiate first with respect to y, then with respect to x. In our other notation, that would just be use a subscript y, then a subscript x. Whereas if we were to take the derivative with respect to y, partial derivative with respect to y, of partial derivative of z with respect to y, that would be d squared z over dy squared. In our alternate notation, that would just be f with a subscript yy of xy. Now, the interpretation of a second derivative is it is the rate at which a rate of change is changing. Now, for a second partial derivative with respect to x, we would know this as the concavity within the xz trace, whereas fyy would be the concavity within the yz trace, which leads us to these two guys right here. If we differentiate with respect to one variable, then with respect to the other variable, what is the significance of this? So first off, we use the term mixed second partial derivatives for these two, where we do one of one and then one of the other. So this would be the rate of change of the rate of change of z with respect to y with respect to x, or with respect to x then with respect to y. So basically, how is z changing as both x and y are changing? So how are those related to each other? The good news is that as long as your function is continuous, we have a very nice theorem by the name of Clairaut's theorem. I might know this as generic French guy's theorem to offset generic Italian guy's theorem when we get to multiple integration. Clairaut's theorem states the following. So if the mixed second partial derivatives are continuous on a domain, we'll refer to that domain as D, then not only are they going to be continuous, but they are in fact going to be equal. This is going to work for any mixed second partial derivatives regardless of how many variables there are in a problem. So for a function of two variables, there are only two options. That would be x and y, so those mixed second partial derivatives would be equal to each other. We will demonstrate this with an example in our next video.